everybody, my name is Devin Cairns. I'm currently a graduate student at Penn State working in the Lee Reactive Water Group. We tend to use reactive transport models to try and understand how catchment characteristics as well as climate affect stream quantity and quality. For my portion of videos, I'm going to be talking about representing subsurface respiration processes, as well as one abiotic process that's important in terms of dissolved carbon. So we'll really be focusing on the three main reactions that we have found with our modeling work that really determine stream carbon dynamics that we observe, especially in catchments where we don't have any carbonate lithology or lithology that could be contributing dissolved carbon to our system. So just want to go over how we can implement shallow and deep reactions, really give a conceptual understanding of the model we will be using. I know this has been covered in some of the other videos in this series. However, it's always good to reacquaint yourself with the model and just remember what the model is doing. So in terms of BioRT-HBV, it really couples together two models, a simple conceptual hydrologic model, HBV, and a reactive transport model that was developed in our group, BioRT. So HBV takes inputs of meteorological data and can output three distinct flow paths that contribute to stream discharge. The first is this surface flow path, or what I like to more think of as a quick flow path. So water that moves really fast through the system, doesn't stay in the system long enough to really be involved in any reactions. The second flow path that HBV generates is this shallow soil zone flow path. And so this would be water that would be more associated with interflow, or water that's more responsive to different meteorological events. And so these reactions, this flow path tends to be involved in more reactions in this shallow subsurface, so shallow soil reactions, and carry more biogenic species to the stream. The third flow path is this deep zone flow path that really represents these deeper and longer flow paths where water stays in the system long enough to be important in terms of reactions that take a longer amount of time. So these reactions would be most associated with weathering reactions, and thus this deeper zone flow path tends to carry more geogenic species to the stream. In terms of implementing reactions with BioRT, it'll simulate reactions in the shallow soil zone and deeper zone. And so again, the shallow soil zone will be most associated with quicker reactions that tend to happen more in the shallow soils. And then you have this deeper reactions, which tend to be slower and more associated with weathering of bedrock. All of these reactions will then produce concentrations contributed to the subsurface. And then BioRT will simulate the transport processes to the stream, where we can combine these flow paths and their distinct concentrations and get our stream discharge and chemistry. So the first process in terms of carbon that I will be covering is the shallow soil zone respiration process. And so when we think of shallow soil respiration processes, especially in headwater mountain streams, this tends to be the largest contributor of dissolved organic carbon to a system. But what is this shallow soil respiration and what does it include? Well, first we think of autotrophic respiration, and second, heterotrophic respiration. So autotrophic respiration is really the respiration that's associated with plants. So when plants respire, they can output CO2 into the subsurface via their roots, and their roots can also contribute dissolved organic carbon via root exudates. Whereas heterotrophic respiration is really associated with the microbial decomposition of organic matter in these shallow soils. And so this decomposition processes, these microbes can break down solid organic matter in the subsurface into smaller molecules, which may then be soluble, which can contribute to concentrations of dissolved organic carbon in the subsurface, or these microbes can fully mineralize these carbon sources to produce CO2, which can further speciate into carbonic acid, bicarbonate, carbonate, and contribute overall to subsurface dissolved inorganic carbon concentrations. However, these autotrophic and heterotrophic respiration processes and how much DOC or DIC each of these processes are contributing to the levels of dissolved carbon we see in our system is really difficult. It's very site-specific, as well as it takes many measurements and many specific and thorough measurements that we often don't have in a system. Therefore, we tend to represent this shallow soil respiration as a lumped respiration reaction. So we consider heterotrophic respiration that consumes the solid organic carbon to produce DOC and CO2, and we get the autotrophic respiration that's happening from roots contributing DOC and CO2. And so we lump these two reactions together by using this A and B term, our stoichiometric coefficients, for how much together the decomposition of solid organic carbon and the contribution of roots produce DOC and CO2. In terms of this reaction, we're really considering the lumped processes that produce the dissolved carbon constituents. And we will equate the amount of CO2 to be dissolved and speciated until it forms, and just consider this as DIC, and not consider the carbonate speciation explicitly. And so when we want to implement the shallow soil, we'll implement it into this, or shallow soil respiration, we'll implement it within this shallow soil zone within our model overall. And so the reaction rate law that we use to represent the shallow soil respiration within our model is the Monod reaction rate law. So really the reaction rate of microbial decomposition of organic matter. And so R represents the effective reaction rate of the production of dissolved organic and dissolved inorganic carbon in the system. K is the inherent rate constant associated with the reaction. C would be the solute concentration of a limiting substrate. Km is the half saturation constant associated with the Monod law. A is the surface area of the reactive mineral. And then we have three different sensitivity functions. First is sensitivity to temperature of the reaction. Second is sensitivity of the reaction to soil moisture. And third is the sensitivity of the reaction to the depth of the water table. However, we do make some simplifying assumptions when we represent the Monod reaction rate law for soil respiration. We assume that there's no limiting substrate in the shallow subsurface. We can assume that oxygen limitation isn't an issue, but that we can also account for oxygen limitation by accounting for this in the soil moisture dependency. Therefore, our final reaction rate law is a product of the reaction rate or kinetic rate constant, surface area of the reactive mineral phase or the reactive organic carbon phase, as well as our three sensitivity functions. That is the end of the first video. And in the next video, we will show you how to actually implement this reaction within BioRT-HBV.